with the concentration of the solute. Okay? And in low concentration, it's linear. So for every 1 osmol, you get minus 1.86 degree. So if you have, let's say, 500 millimolar NaCl, the Na and Cl open up, so it's kind of become 1 osmol, and the temperature of 1 osmol, the melting point, is minus 1.68. So the regular osmometer, this is how we look at the osmometer, how it works. You're taking a liquid, you cool it to minus 6 degrees. Minus 6 degrees is super cool. Then you come with some probe to make nucleation. Then you measure the temperature. If you measure minus 1.86, you report we have 1 osmol. Okay, if you have less than that, you report. So this is how the osmometer works. Okay, and so, but it's not linear all the way. Actually, this nice work that show that in the beginning it's linear, but then later on it's not linear. But I will not go there now. So altogether, the result is table. So the melting point is a function of concentration. Okay? Now, the glass transition is also a function of concentration, but the opposite direction. It starts about minus 140 or 134, something like that, for water, and then it slowly go up with concentration. Now, the red curve, this is the homogeneous nucleation. If you take the small drop, you cool it down, you can go down to minus 40 degrees almost without nucleation. This is the tiny drop. Okay? When you have a bigger volume, it always freezes before that, but this is because you have dirt. But homogeneous nucleation is about minus 40, but when you start to add DMSO or glycerol, the homogeneous nucleation also go down. So if you are in a concentration which the glass transition temperature is above the melting temperature, you can go up and down in temperature and not get ice anywhere, because either you are above melting point or you below glass transition, so no ice. If you go here and you cool it, you will go through this area, and this area is the supercooling. No problem, you can cool something, and there is some good probability that it will not freeze. But when you go below this one, the probability that it will freeze is become very high. Now, if you want to go here, you need to jump across temperatures below the homogeneous nucleation. Now, in order to do that, it's possible if you go fast, doing it fast. So you can jump from here to here in a super fast way. If you have a tiny drop of, let's say, an embryo of few cells, and you shoot it into liquid nitrogen, you can cross this fast enough, not have ice, and you have vitrified. But the trick thing is that you also need to go in the opposite direction fast. So it's difficult to go through this with no ice. So the interesting point is this area. This area, you can go through supercooling directly to the glass transition, because here you're supercooling but no homogeneous nucleation. So you can cool down and get here and no ice. The question, what happens when you go in the opposite direction? and and here the problem is that maybe something in the very low temperature you have some nucleation, and which you do not see it when you wait down. So